Okay, Bismillah. Assalamualaikum and good afternoon, everybody. So this is our first replacement class. So this week we're going to cover asphalt mixtures, and the next class is on Wednesday, our usual time. In that class, we'll also will discuss JKR design method, and finally, our last class is on Thursday, 5 p.m. In that class, we're going to cover some of pavement distresses, okay, damages that can happen to pavements and polymer modified bitumen. Okay. So we have three more classes. That's today, Wednesday, and Thursday. I still have one more assignment for you, but this final assignment is a very simple one. In fact, there is a example in today's lecture that is going to explain that assignment. Okay. However, I'm having a bit of a difficulty with the question because I noticed there's a mistake somewhere. So I need to update the question, and I will put in Spectrum. I think probably tomorrow. So I think you can finish that assignment maybe in at least, I think, a few hours. Within a few hours. Okay. So asphalt mixtures are uniformly combined, mixed combination of asphalt cement, coarse aggregate, fine aggregate, and other materials, depending on type of asphalt mixtures. Usually, this topic is covered by Dr. Suhana. So, but this semester, it is entirely up to me. So I need to come up with my own notes because it's easier for me to use my own notes. All right. So the problem with your batch is that you don't have lab session for asphalt mixtures. Usually we'll have asphalt lab session so that you'll be easier for you to understand. You can see what it meant by coarse aggregate, fine aggregates, and other materials, and also how we mix the asphalt mixtures in the lab. Okay, so I'll just show you the picture. This is the picture of an Marshall mix, asphalt mix that we produce in the lab. Okay, so this mix is a combination of coarse aggregate, fine aggregate, and filler such as cement, and also the most important material, asphalt or bitumen. So there are three main types of asphalt mixtures, which is hot mix, hot laid, meaning that it is mixed hot in a hot environment, and then it is laid on the pavement as with a high temperature. Hot mix meaning cold laid, okay, meaning that it's mixed hot, but when it's laid, it is at a lower temperature. And cold mix, cold laid, meaning that usually cold mix is the one that we mix with um, uh, emulsion bitumen. And when laying also, the temperature is low, so it does not consume a lot of heat. So produce hot mix, hot laid asphalt. This is the most common one that you are going to see. So it is produced by blending asphalt, cement, that is bitumen, coarse aggregate, fine aggregate, and filler. It can be either quarry dust or it can be cement. So the temperature of mixing is ranging from 80 degrees Celsius to 180 degrees Celsius, depending on the type of aggregate. Depending on the type of bitumen. Okay, bitumen that are more viscous will require a higher temperature mixing temperature. The produced hot mix asphalt, HMA lah, normally this is known as HMA, is then shipped and laid at the targeted location. So it is used for high type pavement construction. So it can be, the mixture can be either open graded, coarse graded, dense graded, or fine graded. So describes the types of pavement. Open graded usually is like SMA, and then open graded, gap graded. This is actually gap graded. Open graded, sorry, open graded is porous. Gap graded here is actually SMA mixers. Dense graded can be ACW lah, ACW. Fine graded, I think there is no, we don't use fine graded mixtures in Malaysia, as far as I'm concerned. Okay, mix design involves the selection and proportioning of different material components in order to determine the optimum blend of the different components that will satisfy the requirement. So we have a certain requirement to make sure that our mix achieve a certain strength. So to achieve that strength, we need to vary the amount of bitumen that we use. So the mix that gets the highest strength and other criteria, pre-described criteria lah, okay, prescribed criteria, that percentage of bitumen will be selected as the optimum binder content. Okay, I'll show you how to calculate that afterwards. So job mix formula is the formulation of aggregate gradation and the optimum amount of asphalt cement. So how many percentage of large coarse aggregate, how many percentage of fine aggregate, how many percentage of mineral filler, and then how much bitumen should you add into the mix. So that is the job mix formula. So it gives you the proportion of different materials to be used. Okay. So for normal project, the mixers is just a common ACW14 or ACW20 that you can order directly from the quarry, or you can come up with your own mixture, okay, and then you can actually ask the quarry to produce the specific type of mixture that you have designed. So aggregate gradation in the first phase in any mix design is the selection and combination of aggregate to obtain gradation within the limits prescribed. Usually we only use the aggregate from one quarry, that is the nearest quarry to our project site, or it's possible that we need to use a quarry that is somewhere else, okay, further than our project site. This can be the case when the quarry that is nearby to our site does not have the aggregate that they produce does not meet the specification that we need. For example, in Ulu Langat, there are several quarries. One of the quarries, the percentage of flaking, meaning that the aggregates that are in flakes are very high, the flakiness index. So we cannot use that in some of our projects. For concrete, maybe it's okay, but for designing HMA, hot mix asphalt, it can be problematic. So we need to use other materials from other quarries. So the gradation is used to determine the aggregate particle size distribution. Size distribution is the most important aggregate quality because it determines the interlocking of your pavement. Okay, let's say you have maybe 50% coarse aggregate and then 20%, 40% fine aggregate, and then the remaining are fillers. So if you change the percentage, the interlocking, the design of the interlocking of the aggregate mix is going to be different, and the voids within that compacted aggregate is also going to be different. Okay, so if you use bitumen that is very viscous, you need a different type of aggregate gradation to make sure that the aggregate has the mix has adequate spacing to make sure that the bitumen can actually fill in the gaps, something like that. Or if you want to something that actually have gaps, such as for porous asphalt, you need to use a different gradation so that the void within the mix is very high and it allows water to actually seep through. Okay, so that's the importance of aggregate gradation. So this is the example of aggregate gradation for SMA 20. Like I mentioned last week, SMA is a type of pavement that is used normally at traffic light areas or climbing lanes. So it is a high strength type of pavement. Normally, bukan normally lah, it requires polymer modified bitumen, meaning that you cannot just use typical 60-70 penetration bitumen. You need to modify it with polymer, and it also needs fibers, okay, to make sure that the binder, the bitumen does not drain down. Yeah, it drains from the mix. So this mix is not SMA. This is typical ACW lah. Okay. If this is if it is a SMA, this one is going to show larger aggregate size here. So this is for example, the typical size of sieves that we use, okay, from 19 mm to 0.075. So the design is going to specify the percentage, maximum and minimum percentage, passing percentage. Okay, for example, here for SMA 20, 100% is going to pass the sieve 19 mm sieve, and then 65% passing, minimum passing at 9.5 mm, and 75% passing at the same size. This is maximum size. So between minimum and maximum, you get the middle point here. So to calculate the the amount of aggregates that you're going to use, so you're going to use this midpoint. So this midpoint goes here. So this is 100%, 90%, 70%, 24%. So if passing is 100%, the weight of retain is 0% here. Okay. For 12.5 mm, passing is 90% here. It's given here. You can get from the midpoint. So now 100 minus 90, the retain is 10. Okay. For 9.5, the passing is 70. So 90 minus 70 is 20. So from this percentage, retain percentage, you can multiply it with 1,100 grams, because 1,100 grams is the weight of one Marshall sample. So 1,100 multiplied with 10%, you get 110 grams. Okay, 1,100 grams multiplied with 20, you get 220 grams, so on and so forth. So for the entire one Marshall mix, you're going to have 1.1 grams, 1.1 kilograms. So asphalt content. So this is the challenge to determine the percentage of asphalt that should be used in the concrete mixture. We do not know how much asphalt should we use, because the properties of the aggregate from each quarry can differ. The amount of absorption is different. Okay, lots of things are different lah. If you are using different type of asphalt, different type of bitumen, you also need to have a different calculation for optimum binder content. It's the same lah. Optimum percentage asphalt is the same with optimum binder content. Apa tu? OBC or yeah, the optimum binder content. Okay, so the percentage of asphalt should be within the prescribed limits. We normally test between 5% to 7% asphalt. But in practice, if you say that you're going to use 6% or more bitumen, the contractors are going to moan a bit lah. They say, oh, too much asphalt lah. Yeah, because it's expensive. Asphalt is expensive. So usually we'll try to get our maximum binder content is around maximum 6%. Is okay. But it depends on the aggregate, and it depends on the gradation. It depends on the type of bitumen. So two commonly used methods to determine optimum asphalt content are the Marshall method and the V method. Okay, so the Marshall method described here, since it is more widely used. So this is an example of This is the first example here is for the gradation actually. So table 18.4 give you the specification of the aggregates and mix composition. Okay, this one. So this is the specification that you are given. Okay, this is the type of the size of the sieve. This is a typo, not passive. This is passive passing sieve designation, not passive. Lots of errors in this book actually. Okay, so this is the retain on. Passing on 19, retain on 12.5. Passing on 12.5, retain on 9.5. So the percentage that is passing 19 mm is 0 to 5, passing 12.5, the percentage is 8 to 42. So this is the design that you are given. And then you are also, table 18.5 show you the results of a sieve analysis from the materials available. This. So you have purchased aggregates from a quarry. So normally when you purchase an aggregate, you mention to them that you want coarse aggregate, fine aggregate, and mineral filler. So they'll give you one bulk, several lorries of, depending on your order lah, coarse aggregates, and then they'll give you fine aggregate and mineral filler. Within that mix, you're going to have different sizes. So for coarse aggregate, normally you have the size between 19 until 2 millimeters. It is available in that mix. For the fine aggregate, it can be from here 4.75 millimeters until 0.075. For the mineral filler, you have 0.425 until 75 micron. Okay, 0.075 mm. So you can see that there are overlapping here. In the coarse aggregate, you can have some of the fine aggregates. In the fine aggregate, you can have some of the mineral filler. Okay, so this is normal for quarry punya apa tu purchase. Okay. So the questions ask you, we must determine the proportion of the separate aggregates that will give a gradation within the specified limits. So this is the very easy lah actually. Okay, all right. So looking at this table here, coarse aggregate, total of coarse aggregate 48 to 65%. This part. Total of fine aggregate and filler 35 to 50, and then 5 to 7, which is the asphalt cement. Okay, mineral aggregate, asphalt concrete 90.95. Okay, 5 to 8. Saya cakap ada typo lagi ni. So you focus on here, total cost aggregate 48 to 65. Total fine and filler is 35 to 50. And filler is 5 to 7. It's written here 5 to 7, but it's shown here is 5 to 8. I think there's a mistake here somewhere. This, okay, you just follow this one, 5 to 8. So for cost aggregate, it's between 48 and 65. The middle is 55. So it is actually up to you. If it's given between 48 to 65, it's up to you to give. Maybe you can use this is 48, and here is 49. Okay. The important thing is that the total for cost aggregate, fine, and filler must be 100 lah. Okay. So for this case, in this example here, they give us a range. So 55 is somewhere in between lah. 39 is somewhere in between here. So this is just for the sake of the example. So 55 cost aggregate, 39% fine aggregate, and 6% mineral filler. Next, you need to calculate the percentage of material passing using this formula. So A is the percentage of material passing, capital A, and small a is the proportions that you have chosen just now. Okay, A, B, C. Okay, this is the example here. All right. So this is the table for your calculation. This is table that you have given. This is the midpoint that you have decided, you have chosen. So for 19 to 25, this is 55% multiplied with 5, which is this 5%. So you get here 2.75. So for cost aggregate, you have chosen to use 55%. So all this is 0.55. So this is the percentage from this table over here. Similarly, for fine aggregate, you have chosen here 39%. So 39% multiplied with the percentage here that you are given. Okay, the same thing you repeat for mineral filler. So when you total up everything, you get the total percentage of your gradation, your design gradation. Okay, for 19 passing side sieve 19, retain at 12.5, it is 2.75%. So with passing to 12.5, retain at 9.5, 19.25%. So this is your design aggregate gradation. Okay. So next we need to determine the optimum asphalt content. Okay. So this is the method used based on Marshall method. Marshall is the person that developed this method lah. But this is for HW ni Hotmix asphalt lah. ACW 14. ACW 20, sorry. Okay. For if you are using SMA or if you are using porous asphalt, the method of determining the optimum asphalt content is different, especially porous. For porous asphalt, the way the procedure to determine the optimum asphalt content is completely different. For SMA, it's still the same method. Okay, but porous is different. Okay, so for now, we are going to determine the OBC, optimum binder content. I normally use optimum binder content lah, OBC, for Hotmix asphalt, ACW 20. So we're going to use the Marshall method. So it is described, the ASTM that we use is D1559. Okay, we need to prepare at least 3 specimens where each 3 specimens will have different asphalt content. So you create first three specimen, you normally will start at 5% asphalt. So it is mentioned here, asphalt content spanning from the expected optimum asphalt content between 5 to 7%. Usually it's 5 to 7%. So the first 3 mix, you use bitumen content 5%. Okay. The second 3 specimens, you use 5.5% asphalt content because it's mentioned here, the increment is 0.5. The third 3 mix, you use 6% bitumen. Okay, so the size of this specimen, the Marshall specimen that I showed you just now, the size is 10 centimeter diameter and 6.25 centimeters in height. So the quantity of aggregates having the design gradation is dried at temperature between 105 to 1110. So this is because we are doing things in our lab. We need to make sure that everything is perfect. If we're doing an on-site, of course, the aggregate can be wet, so it can be dried up for just a short time. But in the lab, we need to put it in the oven for between 105 degrees and 110 degrees. Okay, until we have removed all the moisture from the aggregate. So the specimens containing the appropriate amount of aggregate and asphalt are then prepared by mixing and compacting its mixture. So the compactive effort is either 35, 50 or 75 blows, falling at a distance of 50 meters. Okay, the specimen is then cooled and determine the bulk density is determined. So then the specimens are subjected to the stability and flow test. So this is the flow from aggregate. Okay, you have separated your aggregate according to size and weight in each plastic bag, and then you mix all this aggregate that you require for one mix in a tray. You dry it up in the oven, and then here this is my sample. I'm not probably this is my sample. Okay, bitumen. Okay, you add bitumen to the you heat up the bitumen. Sorry, you heat up the bitumen to make it fluid. Okay, because at room temperature, bitumen is going to be semi-solid. Okay, so you need to heat it up. So you transfer the aggregates here into a pan, and then you put in the bitumen. So this is where you can see that it is the actually the pan here is placed on a digital balance, a weighing machine lah, digital balance. So you scoop up the bitumen and you put in just the right amount of bitumen of 5 to 7%. Can be 5%, 5.5 or 6%, depending on the mix that you want to create. Okay, and then you mix it up, making sure here this is the thermometer, making sure the process of mixing is being done at the correct temperature. Okay, and then you put it in the Marshall mold here, and then must stamp it with a spatula, and then put in the Marshall compacting machine. So in this machine, it will be compacted depending on the uh, type of mixers. It can be compacted 35 times, 50 times, or 75 times for each face, for each side. Okay, then it will be compacted like this. The white one here is actually the filter paper to make sure that it does not stick to the Marshall hammer here. Okay, you jack it up, and then you get this Marshall mix. Okay, so this is what I mentioned just now. If you are preparing samples for light traffic, the blows for each side is 55 times. For medium traffic, it's 50 times. For heavy traffic, is 75 times. So this is American standards lah, 18 inch, and the drop is actually 18 inch. And this is number 10. I forgot the weight. Okay, let's see here. Does not specify here the weight of the hammer, but it drops at the distance of 50 centimeters. Okay, so we are lucky nowadays we have this simple machinery that it will lift this hammer. This is the hammer, and this is the mold containing the asphalt bitumen inside here, the mix here. So this hammer will be dropped and compacting this mix in this mold. Okay, in the old times we don't have this mechanism. You need to lift it using your hand. Okay, 50 centimeter, and drop it. Okay, just drop it depending on the how many blows that you want. Okay. At the end of each session, you'll notice that one of your hand is going to be larger than the other because you have developed so much muscle on one hand. Okay, so this is the Marshall test apparatus. So when you have prepared the Marshall sample, you can test it in this machine. Okay, the objective is to get the stability and the flow. In other words, the strength of the mix. So this subject will be the sample will be subjected to loading, and the loading is increased until it reach the deflection drops, meaning the sample breaks. So when the sample, as soon as the sample breaks, the machine will record the maximum loading that is the sample has experienced, and at that loading, what is the amount of deflection or flow that occurs. Okay, how much deflection occurs in the sample, and how much is the loading that causes that sample to deflect, meaning that the sample to fail. Okay. So stability maximum load resistance that the specimen will achieve at 60 degrees under specified condition. And flow is the movement of the sample. Okay, deflection lah, movement of the sample in units of 0.25 millimeters during the stability test. So one flow is 0.25 mm, 1 unit of flow here. Okay, let's see at the cross section of our Marshall mix. So you can see here, in your mix, you're going to have large aggregate, coarse aggregate, fine aggregate, and mineral filler. So this is the total of aggregate. And then you have absorbed asphalt binder. Okay, so this amount of asphalt is being absorbed at the surface of the aggregate. Okay, this part, this dark gray part. And then you have the effective asphalt binder, meaning that the asphalt that is within the mix here, the dark part here. And then you have the red part here, which is the air void that is still available in the mix even after you have compacted it. VMA is void in mineral aggregate, which is the space between the aggregates that is being occupied by asphalt binder and the remaining air void. That is void in mineral aggregate. Meaning that if you don't put the asphalt, VMA is actually the void between the mineral aggregate. Okay, 1 minute, I need to drink some water, sorry. Okay, to calculate the optimum bitumen content, we need quite a lot of formulas. You don't need to memorize because this is just given lah. If it is required in the exam, it will be given. Okay, so first you need to calculate the bulk density of the mix. So you can get the weight of sample in air, and then the weight of some sample in water. So you need to weigh the sample twice. First is in air, another one is in water. And then you need to calculate the bulk specific gravity of the aggregate. Okay, because the aggregate contains voids and all, so you need to calculate the bulk specific gravity. Next is the apparent specific gravity, which is the ratio of weight of air in the aggregate lah, to the weight of equal volume of water. So here PCA is the percentage of coarse aggregate. This is percentage of fine aggregate, percentage of mineral filler. So GACA here is the apparent specific gravity, for coarse aggregate, fine aggregate, and mineral filler. And then you need to calculate the effective specific gravity, which contains here is PB. PB is the asphalt percentage of asphalt by total weight of the paving mixture. Let's say you are trying for the mix of 5% asphalt. Okay, so the 5% is the weight of the asphalt lah. So 100 minus 5% is the percent of weight of the base mixture that is not asphalt. You see in the example afterwards. GMM is the maximum specific gravity of the paving mixtures. Maximum. So this is GMM. Okay. So you need to know the percentage of weight of aggregates, and then you need to know the effective specific gravity first, and GB, specific gravity of the asphalt. Okay. And then not finally lah, you can calculate the asphalt absorption, PBA. So this is very important, especially when you are using different types of materials in your mix. For example, sometimes you are using different types of fillers. You are using fly ash, palm oil ash, kan? So you need to calculate the amount of asphalt absorption, because the percentage of absorption is going to be different in each types of material. Let's say you want to replace the aggregate with glass, or you want to replace the aggregate with plastic, whatever lah, or rubber, for example, rubber crumbs, for example. So you need to calculate the absorption separately. Okay. But normally those things are in a specialized mix for research purposes lah. In industry application, usually this is just straightforward HMA mix. Unless you are working for a very important project in terms of pavement, then there is a possibility that they are going to use specialized mix. Okay, so this type of work, this type of job is not very common, but the probability that you'll be working with this kind of things is not zero. Although the probability is low, quite low, but it's not zero. Okay, you can work at UEM Agenta, for example, in Bukit Beruntung. They have their own research arm, okay, that conducts asphalt research. So it's possible for you to work as a civil engineer in the pavement area. Okay, and then you can calculate. You need to calculate the effective asphalt content, PBE, and then finally, the second last thing, you need to calculate the VMA, void in mineral aggregate. Okay, this is very important. You need to know the void in the aggregate, including the air voids, the volume occupied by the effective asphalt. Okay, this one. Okay, you imagine these are the aggregate mix. The void is in between this aggregate. No asphalt. You assume that there is no asphalt. This is voids in mineral aggregate. The next one you need to calculate is PA here, percentage of air void in compacted mixture. It is also known as VTM. Okay, so what is VTM and PA here is the amount of the void that is still being left in the mix after you have coated the aggregate with asphalt and compacted the mix. Okay, you still have the void in the mix. So this is VTM or PA. So when you have calculated all that, there are several graphs that you need to plot. Okay, we'll go to this graph afterwards lah. Let's look at the example first. So in designing an asphalt mixture for highway pavement to support medium traffic, data in tables 18.9 showing the aggregate characteristics and the table 18.9 showing the data obtained from the Marshall method we use. Determine the OBC for this mix within this, given the specified limits in table 18.7. So this is a table 18.7. This is the specification. You are using medium traffic here, so the number of blows for the specimen is 50, and the flow must be between 8 to 16. If it is less or more or less than this, the range here, the specimen fails. Okay, the amount of air void, be it light traffic, medium traffic, or heavy traffic, it is between 3 to 5%. Okay, this is not used at the moment. Okay, so this is the specification for medium traffic. Is between 10 to the power of 4 and 10 million ESAL. Okay, afterwards we'll look at ESAL. This is equivalent standard axle load. Okay. So you are given these two data. The first is the percentage of coarse aggregate, fine aggregate, and filler. Okay, you have been given this. And this is the specific bulk specific gravity for coarse aggregate, fine aggregate, and filler. And then you are given, these are the data for the samples, meaning that you have already prepared your Marshall samples. You have already weighed the samples in air. Okay, sample number 1, sample number 2, sample number 3. So this is the weight. These are the weights. And then you have weighed the samples in water. Okay, sample number 1, number 2, and the 3. You have tested the samples for stability. So this is 660 kilos, 660, 665. And then from each stability, you have already got the amount of flow for each specimen. However, in this book, the value of flow here is wrong, because this book is actually an American book. So the one that I'm using here actually has been converted to SI, meaning that matrix lah. Okay, unfortunately in this part they have made a mistake. Maybe they have, I don't know, converted wrongly or something. So the values here are completely wrong. Okay, never mind. So this is the GMM, maximum specific gravity for each mixture. So you have tried using percentage of asphalt at 5%, 5.5%, 6%, 6.5%, and 7%. Okay, so at 5%, this is the result. 5.5, these are the results. And this GMM here is the GMM for 5% asphalt content. This is GMM for 5.5 asphalt content, so on and so forth. Okay, next you need to calculate the bulk specific gravity, GMB. So you need to calculate separately for each asphalt content. So 1/3 here, meaning that you are averaging the 3 values of GMB. Specimen number 1, specimen number 2, specimen number 3. So you average it, divide by 3. GMB, weight in air, divided by weight in air minus weight in water. Okay, so you go back to this table here. Weight in air for sample number 1 minus weight in water, 780 here. Okay, and then the weight in air over weight in air minus weight in water. So you calculate for all 3 samples, and then you average it, divide by 3, you get the GMB for 5% asphalt content. So this is GMB for 5% asphalt content. 2.34. Okay. For 5.5%, you repeat the same calculation. You will get the GMB at 2.6. At 6% here, the GMB is more or less 2.48. So this is the GMB for 6.5% asphalt content, and this is the GMB for 7% asphalt content. Okay, so the average bulk density is plotted against asphalt content as shown in figure 18.13a. Okay, let's see here. So this is the unit weight, okay, figure 18.13a, and this is the percentage of asphalt. For every point you need to plot the graph. Okay. Next is okay, similarly, the average stability and flow for each cement content are as follows. So 5%, what is the average stability here, and what is the average flow here? So the average stability here is 61.7, 7 to 6.7. Okay, so you need to average up the values and in this table, 65, this plus this plus this, divide by 3, and flow also this plus this plus this, divide by 3. So you'll get the average stability and average flow. So now we need to compute the percentage of air void. Okay, for each asphalt content, you need to calculate VMA separately. Okay, so 5% asphalt content, GMB is 2.53. Okay, you go back here. GMB for 5% is 2.43, not 53, 43. PTA is 95%. Why? Because you are using 5% asphalt content. So the remaining from 100% is 95% is aggregate. Okay, asphalt is 95%. The aggregate is 95%. Okay, so you calculate the GSB here. This is a percentage of coarse aggregate, percentage of fine aggregate, percentage of mineral filler. PCA is the percentage of coarse aggregate that you have decided earlier in this example. This one. Coarse aggregate 52.3, fine aggregate 39.6, filler is 8.1. Okay, 52.3, 39.6, 8.1 multiplied with 95%, which is this PTA. So the percentage of coarse aggregate is 49.7, percentage of fine aggregate is 7.6, percentage of mineral filler is 7.7%. Okay, so you can plug in the value to calculate the value of GSB for 5%. So this is the GSB 2.69. PTA, you know that it is 95%. So you can calculate the VA, volume in mineral aggregate, at 14.18%. So you repeat all these calculations for 5.5%, you get the VMA. 6% here, you get the VMA. 6%, 6.5%, and 7%. You calculate until you get all the value of VMA. And then a plot of VMA versus asphalt content is being drawn lah. VMA. This one. VMA and asphalt content. So you can plot this. Okay. Next, you need to calculate the PA, which is the void in total mix. Because now you have the void in mineral aggregate. Now you need to calculate the TA or BTM, void in total mix. So this is the formula, maximum specific gravity for the mix, and then you have the GMB divided by GMM. So 5% asphalt content, GMM is 2.54, which is this one, 2.44. So for 5.5%, GMM is 2.56. Let's see here, this is 2.56. Okay, go back to this 5% asphalt content, 2.54 minus 2.43, which is the GMB. GMB, go back to this calculation, 5% GMB, 2.43. Okay, divide by GMM. So you can calculate the PA value for 5%, 5.5, 6, 6.5, and 7%. So this is a mistake in the book. Again, a mistake in the book. Okay. So next, you can use this PA values and plot it versus the asphalt content, and you'll get this one, void in total mix. This graph. Okay. Okay, if you want, you can also plot the flow lah. Flow. You are not going to use all of this graph for to determine optimum binder content. You need only 3, but these other graphs are also useful to for analysis. When you submit the report for the design, you need to have all these graphs. So a plot of PA, okay, you have plotted. So maximum unit weight. Okay, so now you need to find out the maximum unit weight, the percentage of asphalt in the maximum unit weight. So it's given here, it's shown here that the percentage is 6%. So look here, for unit weight, at the peak value, the amount of bitumen is 6%. And the maximum stability here is 5.5%. Let's see. Maximum stability happens here. So the percentage that where you have the maximum stability is 5.5% asphalt binder. And then percentage of air void in figure 18.13E. So in the specification is given the range is between 3 to 5. Let's go back to this specification just now. So the air void here for medium traffic is 3 to 5%. So the midpoint, the average lah, between 3 to 5 is 4%. So in this calculation, you take the average value 3 to 5, 3 plus 5 divided by 2, you got 4%. So at 4%, you get the value of asphalt asphalt mix in the mix is 5.4%. So now you get 6%, 5.5%, and 5.4%. You average up the values, divide by 3, you get 5.6%. So this is the optimum binder content for your mix. Okay, this is the answer, 5.6%. So these are the other properties lah. That is given in apa tu? Compared with the suggested criteria given in table 18.8. Okay. Next, you can calculate the apa namanya amount of binder that is being absorbed. So this is the formula. This is very simple lah kan, because you already calculated all of these specific gravities, different types of specific gravities. You can use all those values to calculate GSE and subsequently calculate the percentage of asphalt that is being absorbed. The value that is different here that you have not been used, that you have not used before is this part, which is the GB. So this is specific gravity of the binder, specific gravity of the asphalt. So normally this will be given. And then you have the GMM, which is the maximum specific gravity for the mix. For the mix that is using 5.6, okay. To calculate this, you need to create your mix at 5.6%. Okay. What you have done here, you have tested the properties of all of these asphalt mix with different bitumen values, different bitumen content. So from all this, within this 5 to 7%, you have actually calculated that the optimum value is 5.6. So the in future mixes, you're going to use this 5.6% as your optimum binder content. You are not going to use this 5 to 7 every differently lah in each time. So you're going to stick with 5.6%. Okay, 5.6%. Okay. So when you create a Marshall mix with 5.6%, you need to calculate again the specific gravity, GSB. Okay, so this is the GSB for that 5.6%. Okay, it's given here. Okay, so these are normally you don't have to worry lah. These numbers will be given. Okay, but what I've mentioned to you is in terms of if you are going to do it in the lab. Okay, so next you need to use these GSE values, calculate the GSB, and finally use the formula GSB. It's a very long one, isn't it? And calculate the percentage of binder being absorbed. Okay, so this exercise is actually easy, kan? But it can be confusing aja lah. Okay, so if you know the ins and outs of these different specific gravity values, then should be okay. But you don't have to worry about memorizing the formulas or what lah. Okay, because everything will be given if the question comes out in the exam. If okay, and then okay, just now is the hot mix, hot late, and then you have this hot mix cold late. Okay, suitable for small jobs. The penetration grade bitumen is very soft. Okay, 200 to 300, using medium curing cutback and also water. This is very rare jobs lah, kan, small jobs. Normally these are for jalan kampung lah, okay, where they use cutback village roads. And then cold mix and cold late. For cold mix and cold late, normally they are using emulsion, okay, where they mix bitumen with water combined with emulsifier, so that the bitumen, the charge of the bitumen is changed and it can be dissolved in water. So when the water evaporates, the asphalt will be left to coat the aggregates. Okay. So the application is seal coat, fork seal, slurry seal, aggregate seal, all of these sealing types of works. It's not really a complete surfacing wearing course. It is being used to be sprayed on the surface of an old pavement. Okay, spray the coat and then put in the you can compact the aggregate, just one layer of aggregate, and then you spray again another layer of bitumen. So that is normally we call it chip seal lah. Chip seal coat is more or less the same. Okay, next is pavement design. Okay, so this method of pavement design has been developed by ASHTO, American Society of State Highway Officials. Okay, ASHTO here. Okay, it is developed during the 1950, between 1958 to 1960s, when at that time the name is Esho. I don't know why they don't have the T transportation here at that time. Okay, so in 1990 they already have changed the name to Ashto. In between this 1958 to 1960, the use of computers simulation that is very basically non-existent. So the way they research, they conduct the study to uh, examine the strength of pavement materials and pavement design is by constructing test loops. They have constructed several test loops. I think next to highway, I forgot, maybe route number 60 lah in the US, if I'm not mistaken. This test loop. So on this test loop, they have constructed different type of asphalt mix, different type of concrete mix. Okay. So they have the military personnel driving trucks that has been filled with concrete. Okay, this truck is being filled with concrete and it's been driven by military personnel. It's been driven, I think, every day, 24 hours a day. So their job is to drive again around and around and around until they get the apa namanya results that they want lah. Okay. So this is very macam nak kata, although it looks not too scientific, but the result is very good because they are actually testing it on real road, not simulation, and they are using real trucks. That's why their method is still being used until today because it's very good test. Although the amount of effort, the amount of money is humongous lah. Okay, to construct this test track and then have the military personnel actually driving day in and day out just to check the performance of the pavement. So the concepts that they use is the pavement serviceability index. How good is a pavement compared with the analysis period. So this is the comparison between the pavement serviceability index compared with time, and this is the loss of the index due to traffic, loss due to swell and frost, okay, because they are actually conducting the test in real situation, so they get the effect of swell and frost, and then this is the total between the loss of traffic and swell and frost. So this is the reduction of the pavement serviceability index. So the scale is between 1 to 5. Okay. So the present serviceability index is usually measured by a panel of raters. So this is how they conduct their tests lah. Okay, they have conducted, the trucks going on, and then they have a panel of raters that will rate the the pavement between 1 to 5. And the accumulated traffic load cause the pavement to deteriorate and serviceability drops. Okay, at some point, terminal serviceability index is reached, and to give you a context, new pavement, normally the PSI rating is between 4.2 to 4.5, and interstate highway can have the TSIs between 2.5 to 3, and local roads have the TSI of 2. This is the accepted lah values of TSI, terminal serviceability index. Okay, before it starts to fail lah. Okay, new pavement with the PSI is 2.4 to 4.2 to 4.5. The terminal one for arterial is 2.5 to 3, and for local road, the terminal one is 2. Okay, less than that, meaning that it's already failed. This is the formula that is being used to calculate the structure number actually. Okay, what you need to do is to calculate this part, the structure number of the pavement. And W18 is the 18 kip equivalent single axle load. So the thing about this method is that it is developed by Americans. So the units used in this formula are all American lah, imperial units. So 18 kips is equal to 18,000 pound. One kip is 1,000 pound. And ZR is the Z test, Z statistic from the normal standard normal curve. And then you have the standard deviation, structure number. The difference between the PSI when it's new and PSI when before it fails. So this is delta PSI. And then you also have the modulus, resilient modulus of the soil. Okay. And W18 handles all traffic standard 18 kip or 80.1 kilonewton loading. So we use this 18 kip as the base one single axle load. Okay, we take 18 kip or 80 kilonewton here as the base single axle load. Okay, I'll show you later lah. So the idea is to determine the impact of any axle load on the pavement in terms of equivalent amount of impact that an 18 kip single axle load will have. Okay, so this is the table for single axle load. Okay, so this is the loading. You can see here, and this is the pavement structural number, and this is the apa namanya equivalent factors. Okay, equivalent factors for different axle load here. So here 18,000 18 kips here. So the equivalent value is 1.0. So this is the base. If the loading for one axle is less, you can see here the factor here is lower. If it is more than 18, the factor is higher. So this is for single axle and PSI 2.5. This is for tandem axles, meaning that in combination of two single axles lah, two single axles. This is normally for heavy vehicles. So these are the factors. Okay, three axle equivalency factors. Okay, what we call here is the equivalency factors for tandem axles. And this is the value for triple axle. So if you can imagine a large truck, okay, you have single axle and in front carrying the engine, and then you have a double tandem axle at the back of the truck body, and then you have series of triple axles where it supports the container. Usually it's like that. So it is a combination of single axle, tandem axle, and then you have triple axles. Okay, but that will it depends on the question lah. Okay? The question will give you probably just single axles, or probably combination of single axle and tandem axles, or all three, single, tandem, and triple axles. ZR is the probability. Okay, don't worry about that lah. You're just going to use this table here. So 95 confident interval, 95% confident interval, and the ZR value here is 1.645. So 90 here and 5 is here, 95. So this is the value for ZR. If you are given the confidence interval is 87, so 80 over here, 7 is here, so 1 and negative 1.126. That is the value of ZR. Okay, Z statistics. Okay. This one, okay. Okay, typical reliability values are between uh, for interstate highways is 90%. Local rates can have a reliability of 50%. Okay. Then this is the S naught, which is the standard deviation. This is very scientific formula, right? And then you have the structural number, where it represents the overall structural requirement needed to sustain the design traffic loadings. And delta PSI is the difference between PSI at beginning of the pavement, initial lah, okay, over the life of the pavement, minus the terminal PSI value. So that is the delta PSI. Okay, all these values are given actually. Okay, MR is the resilient modulus of the soil. Okay. The resilient modulus is determined by a Stowe test method base. And then you have the CBR. You can calculate if you are given the CBR, you can calculate CBR multiplied by 1500, you get the MR. But the coefficient of 1500 here is used when the CBR value is less than 10. If it is more than 10, then you cannot use this formula because the factor here ranges between 750 to 30,000. So if, of course lah, you're going to be the value in your typical question is going to be less than 10. So you can use this formula to calculate the resilient modulus. Okay, this is what I'm saying here is not tips for your final. This is just normal class. Okay, we'll discuss the exam and in the final, the last class on Thursday. Okay, this is how you calculate the structural number. Structural number here, this is the formula, which is this small a here is the coefficient for the wearing cost, and then the base cost and the sub base. D here is the depth of each layers of pavement, okay, wearing base and sub base. M2 and M3 is the drainage coefficient that will be given. So this is the coefficient, small a. This is the small a values. If the wearing surface is using sand mix asphalt concrete, the coefficient is 0.35. If it is hot mix, it is 0.44. So base here is, if it is using crushed stone, what is the value of A here? If the base is using soil cement, what is the value of A? Okay, so all these they have tested in that test track in the 60s. You just imagine. Okay, they have different type of base, surfacing, and also sub base. Sub base, they only have one value of crushed stone, where the value of A is 0.11. Okay. So the drainage coefficient normally is 1. Okay. Thickness. Wearing layers are typically 2 to 4 inches. Sub base and base are between 4 to 10 inches. Okay. This is the nomograph that you can use. Okay. So instead of using the long formula, you can also use this nomograph to get the design structural number. Or you can use this to get the, if you have the structural number, you can use it backwards to get the reliability of the pavement. So in this example here, you are given the standard axle load, W18 here is 5 million. Confidence interval 95%. Standard deviation 0.35. Resilient modulus 5000 PSI. Delta PSI 1.9. And the solution here, structural number is 5, somewhere here. Okay, look at the reliability is 95, start from here. Okay, so you draw a line straight from 95 to this value of standard deviation. So standard deviation is 0.35. Okay, you draw a line until it reaches 0.35, and then you extend this line until it reach this TL line. Okay, from this TL line, where you connect it to the W18 here. So this is W18, 5 million. So from here, you draw a line straight to 5 million and then extend that line until it reach this, then the second TL line over here. Okay, and then you determine the MR here. MR is 5,000 PSI, so this is KSI. So 5,000, you go to number 5 over here. So from here, you go straight to number 5, extend the line until it reach this box. Okay. So from here, you go horizontal, straight, and this line here represents the delta PSI. So delta PSI here is 1.9. So you just draw a straight line until it reach more or less lah 1.9 somewhere here, and then from that point you draw a line, vertical line straight down, and you get the structural number. So this is 4. The middle line here is 4.5. Somewhere in the middle here is 5.5, and this is 6. Okay, so the solution, the structural number is 5 here. Okay, so look at the example. So you are given flexible pavement has a 4-inch sand mix asphalt wearing surface, 10-inch soil cement base, 10-inch crushed stone. Apa tu? These are the thickness lah, the D one, the large D. So it is designed to withstand a 420 kip single axle load and 935 kip tandem axle load per day. The subgrade is 8, standard deviation is 0.5, initial PSI is 4.2, final PSI is 2.5. So you can get the delta PSI from this information. So what is the probability that this pavement will have a PSI above 2.5 after 25 years? So technical coefficient are 1.0. What are the probability that this pavement will have a PSI above 2.5 after 25 years? So what you have learned here is actually within this to calculate the PSI, to calculate the structural number, something like that. Okay. Normally we don't use this method, although it can be used to get the thickness, but for the case of our class, we don't use it to calculate the thickness of the each layer. So in our next class, we're going to use the normal JKR method, and in that method we can get the actual thickness of each layer. Okay, so this is the value that you are given here. It's using sand mix asphaltic concrete for the wearing surface. So the small a is 0.35. For the base is using soil cement 0.2, and the sub base is crushed stone 0.11. So using these values, you can use it to calculate the structural number. So small a multiply with D1, okay, and all that. So M2 and M1, M2 equals berapa ni? Oh, M2 and M1 is Allah. Yeah. Okay. M2 and 1 is 1. Okay, so you calculate the structural number, you get this as 4.5. So the axle load equivalency, table 2 and 3, with structure number 4.5 here. So between this is structure number 4 and 5, between 4 and 5, and you are given here single 20 kip loading. So it is 20 kip somewhere here. So interpolate between, to bawah sikit. So interpolate between 1.47 and 1.51. So for single itself, the value of the single axle load ISAL here is 1.49. So you are also given the tandem load. So the tandem load is 35 kip, and the structure number is 4.5, 4 and 5. Sorry, 4.5. Okay. So 35 kip is between 34 and 36 here. So it's in between, somewhere in the middle here. So you need to interpolate the value, and you get it at 1.24. So total ISAL for 20 kip single axle is 400. This is given in the question, multiplied with 1.49, the ISAL that you get just now. So the total ISAL is 596 for single axle. For tandem axle, the loading that you have given is 900 vehicles, multiplied with 1.24 that you have calculated here, you get here, and the total ISAL for the tandem axle is 1116. So 1116 plus 596 times 365 days times 25 years, you got for 15.622 million W18 loading. 15.622 million times of W18 loading. So as not here is standard deviation has been given, CBR has been given, region of modulus you can calculate. Okay, so you get 12,000. Delta PSI you can calculate 1.7. SN you have calculated at 4.5. So use the nomograph. 15 point W18. Okay, you can calculate it backwards here. So structure number 4.5, go to the delta PSI at 1.7, draw a straight line, horizontal line, and then go to the MR at 12,000, somewhere here, extend this line to this TL line, and then from here, you go to 15.6 million W18, somewhere here, extend this line until it reaches the second TL line, and then go to 0.45 somewhere here. Ni saya buat tak betul lah ni, sebab mungkin dah apa tu, mungkin maybe the ratio of this, the one that I've used in this PowerPoint is not apa tu correct anymore. So from here you go to 0. Mana tadi 45. So this you should extend it straight until it reach the reliability here. So the value of the reliability that you can get is going to be something between 85 to 89%, somewhere here. Okay, so this is the solution using nomograph. You can also use the formula. Okay, so you can key in all the values in this equation, and you solve for ZR here. Solve for ZR. So using this formula, you can get the ZR at 89.7%. Okay, so using this, you get 1.265 somewhere kat sini lah kan, 89 somewhere here, 89.7 kat sini. Alright, so you can interpolate and you get the value of 89.7%. Okay, so this is the examples lah. Okay, the most known pavement group is UAM Agenta. They are a very new group. I have visited their office, their lab, I think maybe 5-6 years back, and everything is brand new. Okay, because they got a lot of UAM got lots of highway project. So it is very viable for them to actually have their own branch of pavement research unit. So all the equipments are very recent lah, very advanced. Okay, so other companies also have their own apa nama ni kat mana Pen Borneo. For example, Opus Consultants also have their own pavement branch. Okay, it is not very not going to be frequent projects or frequent, but you have the probability of working in the pavement area. Okay, guys. Thank you very much. Do you have any questions?
No, Doctor.
Okay, if you don't have any questions, I will upload these notes in Spectrum. Don't forget to sign your attendance. So I'll see you on Wednesday, 10 a.m. That we're going to cover the JKR mechanistic method. That class is very important. Okay, the last two class is very important. Okay, thank you very much, everybody. I'll see you on Wednesday.
Thank you, Doctor.
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 Bye, Doctor.
Welcome.
Thank you, Doctor.
Welcome.